Good. So what I want to do next is Dijkstra's algorithm. Breadth first search. This discussion leads naturally into talking about Dijkstra's algorithm. So Dijkstra's algorithm solves what is called the single source shortest path problem. We'll come back to this problem a couple times around the quarter. So again, you can define Dijkstra's algorithm for an undirected graph or a directed graph. Pretty minor. I'm going to stick with directed graphs. So that's not a fundamental assumption. It's just going to be sort of easier to discuss. And so, like we were just saying, and this is one of those cases where edges have their own properties. Okay, and in this case, they have lengths. And you can imagine lots of things which this length might represent. Nodes might simply be kind of, cities in the states. This length could be, just the physical distance between the two. It could be the cost that it takes to fly from one point to another, so on. Okay? Like in BFS and DFS, we're told that an origin, okay, or a source vertex, which I will continue to call S. And what is the goal? What do we have to do? What we have to do is, for every possible destination, compute a shortest path from S to V. Okay, for every possible destination vertex V. And here, by the shortest path, I mean for which the sum of the edge lengths inside the path are as small as possible. Okay. So for each possible destination, little v, it is our goal to compute. I'm going to use the notation capital D of V, and what this denotes is the length of a shortest SV path in G. Okay? And again, remember, so each edge has a length. A path comprises multiple edges. And when we talk about the length of a path, we just mean the sum of the lengths of the edges in the path. So the shortest path is just the path with the smallest sum of edge lengths. Okay? Notice that need not be the path with the smallest number of edges. Okay, so a path with two edges, each with small length, is better than a path with one edge that has a large length. A special case is when every edge has length exactly 1. Then in fact you are just counting the number of edges in a path. Okay, so a shortest path is just the one with the smallest number of hops, and this capital D definition is just the hop count, okay, or the minimum hop count. All right. And indeed, Dijkstra's algorithm, which I'll describe now, in the special case where all edges have unit length, it is in fact just breadth first search, and that's maybe a good exercise for you to think through after class. Okay, so in some sense it's a generalization of breadth first search to different kinds of edge lengths. Before I state it, two assumptions. One is convenient but not that important, which is that there are paths from S to all of the vertices, otherwise it's sort of degenerate to talk about the shortest path. So for all possible destinations, little v and v, there does exist at least one path from S to V. And the second assumption is the important one, which is that edge lengths have to be non-negative. They cannot be negative. Okay? So several weeks from now, when we talk about dynamic programming, we will revisit the single source shortest path problem, and we'll actually solve it even when you can have negative edge lengths. And so in fact the Bellman-Ford algorithm not only, which we discussed in the first lecture, not only does it require in some sense only local computation, but it actually for free solves the more general problem where there are negative edge lengths. You might be wondering what on earth would be the point of negative edge lengths if you're talking about like distances between cities or something like this. But shortest path problems, like many of these fundamental problems, are good models even of things you might not have thought of right away. Okay, so really a path is just an ordered sequence of decisions. So sometimes you can model picking the appropriate sequence of financial transactions as computing a path in a graph. And then buying something might correspond to a negative length because you're losing money, and selling positive length because you're gaining money. Okay, so there are definitely applications where you care about negative edge lengths. There's many where you don't. Okay, but yeah.
Are you just the cost of zero
so that won't come up. So the fact that looping doesn't necessarily hurt won't bother us. The problem is when looping can help, and that's when negative edge costs come in. Okay, so reasonable question, and if you prefer, go ahead and think about cost as being strictly positive. If somehow your intuition is sharper, go ahead and go with that. But everything I say will be true with this weaker assumption.
What do you restrict when you have negative edges to prevent going back and forth across a negative edge?
We'll get there. Other questions?